The problem I have here is working out the potential of 4 point charges. They all have the magnitude Q, and there are 4 of them, so I might label them Qi. And they are located on the corners of a square in the xy plane. So this is my xy plane measured in meters. They are located at positions 2, 2, minus 2, 2, minus 2, minus 2, and minus 2, 2, which is these positions here. And I want to know what the potential is due to those 4 source charges at the origin, at my point of interest, which is at the origin. So, question is, what is V of R at the origin? We can work this out by remembering the equation for the potential of a number of point charges, which in the SI system is given as 1 over 4 pi epsilon naught times the sum over all source charges. And in this case we've got 4, so I runs from 1 to 4, and each source charge contributes a term Qi in Coulomb. This may be 1 Coulomb in this case, divided by R minus Ri, magnitude of, whereby this magnitude is the distance between the point of interest and the location of the point charge. And we notice that because of the symmetry, in this particular problem, those distances are all the same, and they are easy to calculate because this is the right angle, so we can use Pythagoras to conclude that they are all of the order that they're all equal to R minus Ri, in this case, in all cases, is equal to the square root of 2 squared plus 2 squared, which is the same as the square root of 8. And I've also taken advantage of the fact that we're interested in this case in the origin, so therefore R is equal to that. If I then substitute, I can work out that the potential at the origin is equal to 1 over 4 pi epsilon naught times 4 times Q, which may be 1 Coulomb, divided by the square root of 8. You see that this cancels, and we then obtain as our final result that the potential at the origin is Q divided by pi epsilon naught, which is the dielectric constant. We are therefore dealing with a problem in vacuum, or in good approximation it could also be a problem in air, times 1 over square root of 8. And since I talked about 1 Coulomb, if we've got 1 Coulomb, then there's another 1 here. The distances are in meter, so the unit of this would be volts. This is the potential of the origin. And we note that the potential at the origin is finite. in fact, if we've got positive charges, this is positive, these other three numbers are positive, we've got a finite positive. The potential at the origin is finite and positive. That's our conclusion. Now this is interesting because if we now look at the field, we have four contributions to the field. We have a field vector due to this source charge Q1, which will point in this direction. We will have a contribution from this source charge Q2, which points in this direction. And we have one from Q3 pointing at the same magnitude into this direction. And finally, from Q4, a field contribution pointing in that direction. So this is E4, this is E1, this is E2, and this may be E3, the one which is missing. And if we work out the net electric field, then that is equal to 0. So you can see that the field, the electric field, can be 0 although the electric potential at the origin is finite and positive. This is possible because the electric field is always equal to the negative gradient of the potential. E is equal to minus gradient of V. If we illustrate the situation in this particular case, we draw again the x, y plane and also include now a z-axis. Our charges are located on the corners of a square as before, and they are in these positions. Indicated here in blue. There's 1, 2nd, 3rd and 4th. Now we've worked out that due to those four charges we have a positive potential somewhere on centrally on the z-axis, which might be this green point here. As we approach each of the corners, the potential will go up. So for example, it goes up like this, it goes up like that. It will, in order to illustrate it, let me draw another box in perspective so that we can nicely see the situation. And from here it'll go up like that, and from here it'll go up like that, and we have these curved planes and you can see what's happening here. So this is the nadir of this point where the gradient is 0. Gradient is 0 is the nadir of some kind of a concave surface looking from the top. So convex looking from the bottom, and looking from the top it's the convex surface. Gradient is 0 at the nadir of a concave surface that is the potential surface. And that explains why at that point the electric field is zero. So therefore at the origin E is equal to the zero vector.